Welcome to our first session where we're going to have a fairly quick review of multiple linear regression on topics that you have covered in Biostat 1, but I might be covering them with somewhat different terminology that I want to get you familiar with. So we're going to cover continuous and categorical predictors, interactions, analysis of variance tables, and model formula. Now I'm breaking up the regression model into two parts. In this first part that I referred to as the systematic part, we are modeling only the expected value of our outcome variable y for given values of the predictors x. And that is modeled as a sum of these predictors, which consist of coefficients, beta 0 being an intercept, and beta 1, beta 2 being the regression coefficients for each of the predictor variables x1 and x2. In the second component, the random part, is where we account for random errors. So this is showing now the complete prediction model for the observed values yi as a sum of this systematic part that we saw on the previous page plus these so-called residuals, epsilon sub I. And this is just the same thing written out using the formula from the previous page. So this regression model, along with this assumption, is a very compact way of writing out both the model and its assumptions. The assumptions are written out as epsilon I, the residuals, are independent and identically distributed according to a normal distribution with mean 0 and constant variance sigma squared. And this contains four assumptions of the multiple linear regression model. The first is that the residuals are normally distributed. It's not the x, the y, it's the residuals that we assume are normally distributed. We assume that they have a mean of 0 at every value of the predictors. That means that it's an unbiased predictor. It doesn't tend to overpredict or underpredict for different values of the predictor. It's always equally likely to be positively in error or negatively in error. The third assumption here is that there is constant variance at every value of the predictors. This is called the assumption of heteroscedasticity. And then finally, the observations, the values x, y, and the residuals are statistically independent, meaning every observation is independent of each other. Now the x values can be continuous or discrete. For continuous predictors, they can be coded as is, or they might be scaled to unit variance, which results in so-called adjusted regression coefficients. And the interpretation of these for as-is coding is that an increase of 1 unit of the predictor results in this much difference, that is the value of beta in the continuous outcome variable. If they were scaled, then the interpretation would be that an increase of 1 standard deviation of the predictor results in an increase of beta in the continuous outcome variable. And this is what we call an additive model. It's additive because adding something to any of the predictor adds to the outcome variable with an amount just multiplied by the coefficient beta. For binary predictors, that is discrete or categorical variables with 2 levels, they are recoded internally or explicitly as a so-called indicator or dummy variable, that is 0 and 1 coding. And the interpretation for those is that the increase or decrease in the average outcome levels in the group coded 1 compared to the reference category, which is coded 0, is the value of beta. So for example, in this simple linear regression model where the expected value of y given a single predictor x is beta 0 plus beta 1 times x, where x equals 1 if a subject is male and 0 if female, then the interpretation of beta 1, it would be the difference in whatever this y variable is, let's say height or weight, between males and females on average. Now for multi-level categorical predictors, let's say something like neighborhood or hospital, if there are k values of that predictor variable, there are k minus 1 dummy variables in a recoding of it for regression. So if we have 10 neighborhoods, there would be 9 dummy variables. And the interpretation is just like it was for a binary variable, but with each of the values of the multi-level categorical predictor compared to one reference category. When we're testing significance of a multi-level categorical predictor, the default test that you will see for a given regression output will only be for one value at a time. And in order to test for significance of association between an entire categorical predictor and the outcome, you'll have to use something like a partial F test in a nested Anova. And there will be an example of that in the lab today. Just as a note, Stata and R code dummy variables automatically and behind the scenes, so you don't actually have to worry about that, which can be a good thing and a bad thing. It's a good thing if it does what you want. It can be a bad thing if you're not sure what's going on and not sure how to interpret the output. In SAS, you have to do it explicitly. But I would note in R that you have complete flexibility over how it is done. For performing inference from multiple regression, and by inference, I'm talking about inferring something about a population from the sample, and typically whether there is an association between one of the variables and the outcome. A common approach is to take advantage of this property that linear regression coefficients are t-distributed when the assumptions are correct. So under the null hypothesis that there is no association between a predictor and the outcome, that coefficient will be t-distributed, and that gives you a way to perform a hypothesis test against the null hypothesis of the coefficient being 0. Then the variance in the estimates from each coefficient are calculated and used in this t-test against the null hypothesis of the coefficient being 0. And that, for a single coefficient, can be interpreted as a test of whether this predictor x1 predicts y while holding other predictors constant. And that holding other predictors constant is a property often used in causal inference to control for confounding, as there's some discussion of in 4.4, and we'll talk a little bit about in this course, but you will hear a lot more about in your Epi2 class. Interactions between two of the predictor variables are modeled as the product of two of the covariates or predictors. So in this systematic part of an equation, the expected value of y for a given value of the predictors x, we have the intercept, beta 1 x1, beta 2 x2, and then we have a third coefficient that's called beta 1 2 here times the product of these two variables, and that's an interaction between the variables x1 and x2. Just to give a little example of what interaction is, these are some examples of interaction and non-interaction between the amount of coffee someone drinks, 1 cup or 3 cups, the amount of time to complete a task in minutes, and whether it is morning or evening. So this first example is one where drinking 3 cups of coffee makes you complete the task faster, and also it being evening helps you to complete the task faster, but there's no interaction between amount of coffee and morning or evening, because the effect of morning or evening is the same whether you've had 1 cup or 3 cups of coffee. Or put another way, the effect of time of day is the same at 1 cup or 3 cups of coffee. I'm not sure if I said the same thing twice there, but either way, there's no interaction here between time of day and amount of coffee. Same in the second plot. Here, coffee has no effect, but time of day, morning or evening does, and that effect of the time of day is the same, regardless of the amount of coffee. This third one's kind of an interesting example because in this example, the amount of coffee, its effect is dependent on the time of day. And there is an interaction here because we see these lines not being parallel. So in this case, if we were just to look at the amount of coffee without considering time of day, we would actually see no main effect of the amount of coffee. And similarly, we would see no effect of the time of day if we were just averaging across 1 and 3 cups of coffee. So we actually have to look at both the main effects of coffee drank and time of day in order to see that both of these do matter and they depend on each other. These last 3 are additional cases of there being an interaction, which is evidenced by these lines not being parallel. So in all of these, the effect of amount of coffee or the effect of time of day is dependent on the other variable. Now, I don't want to get into the Anova table in too much detail, but I want to point out that these first 2 rows, the model row and the residual row, correspond to those 2 parts of the model that I wrote out before. Model being the systematic part and residual being the random part or the residuals part. Now, for each of these in the Anova table, there's a calculated sum of squares, degrees of freedom, and then a mean sum of squares that is just dividing the sum of squares by the degrees of freedom. And the F statistic is a ratio of these mean sum of squares of the model divided by the mean sum of squares of the residual. So you can imagine that if the model explains a lot of variation and there are little residuals, then you're going to have a large value of F. And conversely, if the model is mostly random and explains about as much variation as the residuals, then this value of F is going to be something close to 1. And that is the basis for an F test. If you have a value somewhere close to 1, then that's consistent with the null hypothesis of the model not being a useful predictor. And if you have a very large value, that's inconsistent with that null hypothesis. Now, in R and other languages, the workhorse for how you're going to do a lot of regression is with the model formula. So I'm going to give just a brief tutorial to the model formula here. And in R, it will help you across many, many packages. So functions in base R such as AOV for analysis of variance, LM for linear model, GLM for generalized linear models, and Cox-PH for Cox proportional hazards survival models, they all use a model formula interface. Now that formula determines what model is going to be built, the systematic component of it, by the R procedure. And the basic procedure is the response variable is described by the explanatory variables, with this little tilde here being read as is modeled by, or is modeled as a function of, or as described by, like I just did. So for a simple linear regression, it's just y as modeled by x. That's all. Where x is the explanatory variable and y is the response variable. Then it's easy to add additional explanatory variables and turn this into a multiple linear regression, y as described by x plus z. Noting here that plus does not mean addition like usual. It means that we are adding it to the model. If you actually wanted to add x and z and use this compound variable as a variable, you would have to use this I, which stands for identity, as with x plus z around it. And this would create a new variable that was the sum of x plus z. But normally you're going to do this. Just we want a model that has x and z as explanatory variables. So in a multiple linear regression model, which we use LM for, so this is with a continuous variable y, if we have tilde u plus v, this is a remarkably simple and powerful interface. Using this one model formula, this can be several different types of regression. If u and v are both factors, this would be an analysis of covariance. If they're both continuous or numeric, this is a multiple regression. And if one is a factor and one is numeric, this is an analysis of covariance. And all of that is just determined by the type of variables that u and v are. So this is a powerful but also a little bit scary feature in that this one formula can give you all of these different types of regression. And this is why one of my colleagues, I remember once saying, which made me laugh, that giving beginner students R and telling them to do regression was a little bit like handing a chainsaw to a new student. So it'll be supervised use of a chainsaw here, and hopefully no one will hurt themselves. So here's a little cheat sheet about model formula. So as we saw on that previous page, plus just means to include another variable in the model. Minus means to delete a variable from the model. Colon means to include an interaction between x and z here. This asterisk, the times, is a convenient shorthand for including both the variables x and z and their interactions. The slash can be used for nesting in a hierarchical model, and the pipe here can be used for conditioning in a mixed effects model. And we will talk about this later in the course. This caret here is for including interactions only up to a certain level. So in this case, this is to the power of 3 includes u, v, w, and the interaction of u by v by w. So in this case, it's all of the interactions. So it could also be accomplished by u times v times w. And then finally, this is a rarely used option, but -1 means to delete the intercept. So how to interpret the following model formula? This first one includes 3 variables, u, v, and w, plus the interaction of u with v, u with w, and v with w. So this is all of the two-way interactions. The second one, u times v times w, that would be including the 3 variables plus all of their two-way interactions plus the 3-way interaction. But doing minus u colon v colon w takes away the 3-way interaction, so it's actually the same as above. And in this final formula, we have u, v, and w, and the caret 2 says to add all of their two-way interactions. So it is again another way of saying the same as the previous 2. So in fact, all 3 of these are the same. So now we have u, v, and w. We have the two-way interactions and a 3-way interaction, which is the same way as saying u times v times w. This is just a shorter version of saying what the first is saying explicitly, and is also exactly the same as the third line, which says to include u, v, and w and all the interactions up to 3-way. And that brings us to the end of the first lecture. Congratulations. If you go ahead and do the quiz right now, I'm sure it will only take you, 5 minutes. It's 5 questions, and it is on the things that were directly just covered in this lecture, so I encourage you to go ahead and do it right away. And then after that, take a look at the lab materials for this week. Thanks for watching, and I'll see you next week.